Hello, welcome back to Learn Physics. In today's topic, we are going to discuss about the rest of the portions in magnetism and matter. I told you in last video itself, we will be doing about the torque acting on a magnet. So what will be the torque acting on a bar magnet which is present in a uniform magnetic field? Okay. So, here it is the torque acting on a bar magnet which is present in a uniform magnetic field. What will be the torque acting on a bar magnet which is present in a uniform magnetic field? Usually the children won't be knowing what we should write for particular question because they are not understanding the question properly. Here are you clear now? We are going to find out the torque acting on a bar magnet which is present in a magnetic field. Bar magnet is present in a magnetic field. So first I am considering a magnetic field, uniform magnetic field. It is north-south. If it is uniform, how we will represent? With the parallel lines. North to south with equal distance, we will be representing the magnetic field lines. So B is acting in this direction. Here a bar magnet is present. Okay, a bar magnet is present in this north-south. Okay, now, so in the magnetic field, a bar magnet is present means anyway the torque will happen, rotational effect will happen. What will be the value of magnetic field? So, here first I am going to consider what will be the force acting on north pole. What will be the force acting on north pole? It will be acting in this direction. It will be MB. This one we already learned, isn't it? So it is MB. Okay. And what will be the force acting on south pole? M is the strength of the magnet. So it is acting in this direction, opposite direction, minus MB. Okay. So M is the strength of magnet. So strength, pole strength. We can say M as pole strength. That is this side. What is the strength of this side? Okay, that pole. M is the pole strength. Now, so two equal and opposite forces are acting, are parallel, equal, and they are, yes, it's acting in opposite directions. Direction is opposite. But they are parallel forces. MB and minus MB are parallel forces. It is opposite direction, but their magnitudes are equal. So that will give a couple, isn't it? A couple is there, so it can create a rotational effect. It can give a rotational effect. So the torque acting on the system, how we can find out? Torque will be equal to one of the force into perpendicular distance between the two forces. What is the perpendicular distance between the two forces? So if I am drawing one line like this will be, see, I am representing it as A. NA is the perpendicular distance between these two forces, isn't it? So force into, what is the force? MB into, what is the perpendicular distance? NA. Now we are going to find out the value of NA. How we can find out NA? See, if this is theta, what is in that triangle? Let's see, SAN. In that triangle, what is sine theta? Opposite side divided by hypotenuse. What is the opposite side? NA divided by hypotenuse is NS. What is this NS? NS is the length of the bar magnet. What is the length of the bar magnet? The length of the bar magnet is given as 2L. Because in last class also we took that length as 2L to get the minus L to plus L, isn't it? So here also we are continuing in the same way, 2L. That is very easy for the calculation, that's all. Okay, so what is NA? NA will be equal to NS into sin theta. What is NS? It is 2L sin theta. So what we are getting over here, torque tau equals MB into 2L sin theta. What is this M into 2L? Magnetic moment. M capital M, B sin theta. So it will be equal to M cross B. Torque tau equals M cross B. Understood how we are writing? So small m represents the pole strength. Capital M represents the magnetic moment. Okay, magnetic dipole moment is M capital M into B sin theta will be equal to torque acting on the system. Therefore, torque tau equals M cross B. Clear? Okay, now using this formula also we can define the value, the magnetic dipole moment. How we can define magnetic dipole moment from this equation? See here, if I am considering torque tau equals MB sin theta, if theta equals 90 degree and B equals 1 Tesla, then we can write it as torque tau equals M. That is, magnetic dipole moment will be equal to the torque acting on the system if it is both are perpendicular to each other and having a magnetic field of unity. If magnetic field is 1 Tesla and magnetic moment and the magnetic field both are perpendicular to each other, then we can say torque acting, the magnetic moment will be equal to the torque acting on the system. Okay, magnetic dipole moment, in that way also we can define. Okay, so clear all of you? So next we are going to find out how we can find out the magnetic field of or magnitude of magnetic field using a compass needle. Okay, next is we are going to find out the magnitude of magnetic field using compass needle. Okay, we have a compass box with us. Using that compass box, how we can find out the magnitude of magnetic field? So a magnetic field is here. Uniform magnetic field is here. There a compass needle is kept. What will happen? North south or north south direction, a compass needle is there. What will happen there? Yes, torque will be acting on the system. It will try to rotate, deflect. That is, it is a rotating effect is there. Rotating effect is there means a torque will act on the system. What is the torque acting on the system? Torque tau will be equal to M cross B, that is equal to MB sin theta. Okay, so there is a rotation, it is deflecting or torque is acting on the system. Because of this torque, restoring torque will be acting on the compass needle, isn't it? That restoring torque acting on the system will be, what will be the value of restoring torque? The restoring torque acting on the system will be equal to, restoring torque will be opposite to the applied torque, isn't it? We know restoring force will be opposite to the applied force. So suppose I am giving a force on the spring. What will happen? That is my applied force. But the spring will be having the tendency to come back. What will be that force acting on the spring to come back to the original position? Whatever I applied, the same force will be there but in the opposite direction. I am applying it to extend, but the restoring force acting on the system will be coming back, isn't it? So it will be opposite in direction. So here restoring torque will be opposite to the applied torque. So it is minus mb sine theta. So it is having rotational effect. But we know torque 2 equals I alpha. Like that one formula we know, right? I is the moment of inertia of the system. And what is alpha? Alpha is the angular acceleration. In terms of theta, if I am writing, it's alpha omega equals theta is angular displacement. D theta by dt will be omega, and d square theta by dt square will be equal to, what is d omega by dt if I am considering, that is called alpha, isn't it? So instead of omega I can substitute as d theta by dt, so we will get it as d square theta by dt square, that is equal to alpha. Okay, so instead of alpha I can write it as d square theta by dt square. Now I am substituting it over here. I will get it as I into d square theta by dt square, that is equal to minus mb sine theta. Okay, if theta is very small, we can consider it as minus mb theta also. Sine theta is nearly equal to theta. I can consider like that, and d square theta by dt square will be equal to minus mb by I into theta. Since we are considering theta as very small, so sine theta will be nearly equal to theta. So this equation which it represents, yes, it is the oscillation, isn't it? From here we can find out the value of t, time period, while we are comparing it with the d square theta by dt square omega square into x. Okay, if we d square x by dt square equals minus omega square x. So what will be the value of t here? T equals 2 pi by omega. Omega is root of mb by I. Okay, this one you are remembering, right? In last year you would have learned about the oscillation. D square x by dt square equals minus omega square x, isn't it? So t equals 2 pi by omega. In place of omega, here it is root of mb by I. So we will get it as 2 pi into root of I by omega. So here how we can find, our aim is to find out the magnitude of magnetic field. So I am squaring both the sides. I will get it as t square equals 4 pi square I by mb. So what is b here? From here we can write b as 4 pi square I divided by t square. So that knowing the value of I, m and capital T, we can find out the value of B. This is how we will be finding out the magnitude of magnetic field using a compass needle. So magnetic field is present in a uniform, compass needle is present in a uniform magnetic field. So we are going to find out the magnetic field. Otherwise also we to find out the value of magnetic field, isn't it? But this is using a compass needle, how we can find out the magnetic field. Okay, clear? So torque acting on the system is, we are starting from the torque, and from there we are calculating the restoring torque acting on the system. Okay, and then we considered the equation for oscillation, and we got the value of t equals 2 pi by omega, and from here we are getting the value of b as 4 pi square into I by mt square. Okay, clear? So next we are going to study about the potential energy of a magnetic dipole. How we can find out the potential energy of a magnetic dipole? See, in a magnetic dipole. Dipole, you know, right? North and south pole. So these two poles together, we will say it as separated by a distance. So it is called a magnetic dipole. What is the potential energy? How we can find out the potential energy? To calculate energy, what we will do usually, we will find out the work done. What is the work done in rotational effect? Work done will be equal to 2 d theta. That is the work done, isn't it? So for that also, first we need the torque. Torque acting on the system. mb sin theta is the torque acting on the dipole. Isn't it? Present in a uniform magnetic field. Torque equals mb sin theta. And we need, if it is rotating through an angle d theta. If the dipole is deflecting through an angle d theta, then what will be the work done for that small deflection d theta? dw will be equal to tau into d theta. Okay, what is tau here? mb sin theta into d theta. This is the work done for a small deflection d theta. Then what will be the total work done if the dipole pole is moving from theta 1 to theta 2? If theta is moving from theta 1 to theta 2, then what will be the total work done? That will be equal to integral theta 1 to theta 2 mb sin theta d theta. Okay, that is total work done. How we can integrate? That is equal to, for a particular magnet, m and b are constant, mb into integral theta 1 to theta 2 sin theta d theta. What is integral sin theta? Minus cos theta. Integral sin theta is minus cos theta. So it is minus cos theta, up lower limit, upper limit. So applying the upper limit and lower limit, what we will get? Minus mb cos theta 2 minus cos theta 1. Okay, so we can write it as mb into cos theta 1 minus cos theta 2. So this will be the potential energy. This work done will be stored as energy in the dipole. So that energy, that will be equal to the potential energy. So potential energy of the system will be equal to U. Representation is potential energy representation is U. That is equal to mb cos theta 1 minus cos theta 2. Okay, so suppose if the angle is, so we can consider the different cases now. When theta 1 is theta 1 to theta 2. From theta it is deflecting till 90 degree deflection. What will happen? So if theta 1 equals theta and theta 2 equals 90 degree. Till 90 degree it is deflecting. Then what will be the potential energy of the system? Potential energy U equals mb cos theta. Instead of theta 1 we can write it as cos theta, and theta 2 cos 90 is 0. So will be equal to mb cos theta. So the potential energy U equals mb cos theta, and that is, we can represent it as m dot b. U equals m dot b. So if m and b are perpendicular to each other, if m and b are perpendicular, what will happen if m and b are perpendicular? Potential energy U will be equal to, see, perpendicular means theta is equal to 90 degree. Cos 90 is 0. So potential energy will be 0. If magnetic moment, magnetic dipole moment and magnetic field are perpendicular to each other, then potential energy will be equal to 0. Then if they are parallel to each other, if m and b are parallel to each other, what will happen? It is 180 degree, isn't it? If they are parallel, we can write it as theta is equal to 0, not 180 degree, 0. M and B are in the same direction, then only it is theta will be equal to 0. Then if cos 0, that will be equal to M into B. Not M dot B, it will be M because 0 is 1. And in the same way, if M and B are anti-parallel, having an angle 180 degree, then we can say U will be cos 180 is minus 1. So minus MB. We will get it as potential energy is minus MB. So this is for the unstable equilibrium, and U equals plus MB is for stable equilibrium. So U equals MB is for stable equilibrium. That is, it has, why it is called as a stable equilibrium? Because it has energy is, maximum energy is there. So it has stable. So it is very minimum. Negative energy means it has to come back to the stable equilibrium. So it has minimum energy is there. So it is minus MB. Energy is negative. That is why we are calling it as unstable equilibrium. Okay, clear for you this one? So I hope all of you understood all those things, and if you like the channel, please don't forget to subscribe, like and share. Okay, thank you for watching. Bye.